Year 1 Further Maths, Sequences and Series, Lesson 1, Using Standard Results. So let's identify what we actually mean by standard results for summations. And let's start by thinking about summations. So let me give you an example. If I wanted to work out this means that I am substituting in successive values of r and then taking a sum from r equals 1 to r equals 5. So if r equals 1, then 2r is equal to 2. If r equals 2, then 2r equals 4. If r equals 3, 2r equals 6, 8, and 10. And then the sigma tells us that we need to add together these terms. So this comes to a total of 30. And that's what we mean by a summation. You've done quite a lot of work on this previously. Now, what do we actually mean by standard results for summations? Let's start with the simplest standard result there is. We are going to sum between r equals 1 and n the terms of this sequence. Now, look at the formula here. It's not actually dependent on r. So all this means is that we're adding 1 n times. And this, of course, means we have a total of n. If you add 1 together n times, you get a total of n. And that's the first of the standard results for summations. Very, very simple one. The next standard result of a summation is if you add together the terms of this sequence. So this would mean you're adding together 1, 2, 3, all the way up to n. Now, what is this equal to? This is equal to a half n plus 1. And we're going to prove that in a minute. Now, there are two other standard results for summations which we're going to write down. The next is if you want to add together square numbers. So 1 squared plus 2 squared, all the way up to n squared. This is given by this formula. N over 6 multiplied by n plus 1 multiplied by 2n plus 1. And the last standard result that we will cover is if we're adding together the cube numbers all the way up to n cubed. And this is given by n squared over 4, n plus 1 all squared. Now, these two results can also be proven, but we are going to prove them a little bit later on in a further lesson. The first one is a fairly obvious result here, and this one we are now going to look at proving. So let's look at this result. We want to prove that this summation is equal to a half n plus 1. So let's look at the actual summation that we are carrying out. We are adding together 1, 2, 3, all the way up to n. Now, you should recognise this as an arithmetic progression or an arithmetic series. Now, we know that the sum of n terms of an arithmetic series is given by the formula Sn equals half n 2a plus n minus 1 d, where d is the common difference and a is the first term. Now, you've proven this result previously. We're not going to prove it again. We're just going to make use of it. So our summation here, our series total is equal to a half n, well, there's n terms, 2a, the first term is 1, so that gives us a 2 here, plus n minus 1, and of course the common difference here, d, is just equal to 1 as well. So we have this. Now simplify this and we get a half n plus 1. So we've proven this result here. Now we can also prove the results for the sum to n terms of these two series, but as I said previously, we're going to do this in a later lesson because we need a little bit more maths before we're ready to understand these proofs. So here's a quick summary of the 4 standard results that we are going to make use of in some of the questions that we're going to have a look at in a minute. You do not need to memorise these results, they are given in your exam formula booklet, but do be familiar with them, and as I always say, the more that you can memorise, the easier that these things will be at your fingertips when you need to use them. So let's take a look at an example. We're going to use standard results to find this summation here. So the first thing I'm going to do is expand my brackets. So we are finding the sum of r cubed plus r squared between r equals 1 and n. Now we can split this up into 2 summations, the sum of r cubed between r equals 1 and n, and the sum of r squared between r equals 1 and n. We're allowed to do this because we're just adding terms together. So rather than cubing and then squaring the r value and then adding them together, we're doing the cubing and then the squaring and then adding separately like this. So this is a perfectly legal separation here into the 2 summations. So we're now going to use our standard results. So the sum of n cubed numbers between r equals 1 and n is given by the result a quarter n squared n plus 1 squared, and the summation for r squared was 1/6 n plus 1 to n plus 1. And that could be an answer, but it's not a very neat answer, and we're going to try and factorise this carefully by looking for common factors which we can factorise. So look at the quarter and a 1/6. I'm going to take out a factor of 12, 1/12. We can also take out a factor of n and another factor of n plus 1, common to both terms. I'll use large square brackets for clarity here. Now over here I'm going to be left with a 3, so that multiplies back by the 1/12 to give me a quarter. I want an n here, and I want an n plus 1. Always double check by multiplying back. And then in the second part I would like a 2, so that I have 1/6 when I expand. I then need just a 2n plus 1 term. Here we go. And then I'm going to simplify the contents of the brackets. So that gives me 3n squared plus 7n plus 2. And always check, because I have a suspicion this quadratic in blue will also factorise further, and will factorise down to give us 3n, n here, and I think we're going to have a 2 and a plus 1 there. So 3n plus 1, brackets n plus 2, and there's our final answer. Now, the beauty of having this generalised summation is if, for example, we then wanted to find the sum of r squared bracket r plus 1 between r equals 1 and 5, then all we would have to do is substitute n equals 5 into this generalised result here. And this gives us an answer of 280. And having a generalised result allows us to calculate various different summations using any n value. Let's take a look at another example. We're going to use standard series formulae to show this result here. So as we did previously, let's expand the brackets. So we've got 3r squared minus 4r to the power of 3. And let's split this up into two summations. I can also take the factors at the front outside of the summation like this. Now, just in case anyone's not sure about why we're allowed to do that, let's take a simple example up here. Let's imagine I was working out the sum between r equals 1 and 5 of 3r, like this. Well, that's 3 times 1 plus 3 times 2. I'll put these in brackets for clarity, even though the brackets don't really have any mathematical meaning here. 3 times 3, 3 times 4, plus 3 times 5. Now I can factorise out that 3, so I have 3, and then 1 plus 2 plus 3 plus 4 plus 5. And you can see that the two calculations are the same, and this can of course then be rewritten as 3 multiplied by the sum of r between r equals 1 and 5. So all we're doing is taking the factor of 3 out. So we add the terms together and then multiply by 3, rather than multiplying each term by 3 and then adding them together. It's the same concept. And it just simplifies some of the notation a little bit. So we have 3 here. Now our generalised result for the sum of r squared is, of course, 1/6 n plus 1 to n plus 1. And then we want to subtract 4 multiplied by our generalised result for the sum to n terms of r cubed, which is n squared over 4, n plus 1 all squared. So we get a little bit of simplification here. This becomes a half n plus 1 to n plus 1 minus n squared, n plus 1 squared. Now it's a show that question, so we need to make sure we end up with the correct answer at the end. We've got something to aim for. Let's factorise out common factors, including this fractional coefficient here. So we're going to take out a half, n and n plus 1. So large square bracket here for clarity. What do we have inside the square bracket? Well, for the first part, we're going to need a 2n plus 1. And for the second part, well, I'm going to need a 2 to cancel with the half and create 1. I then want an n and an n plus 1. Always double check as you work through these. And then finishing this off, we've got a half n, n plus 1, and then inside the bracket, how does this simplify? Let's see. Well, we've got 1 minus 2n squared. The n parts cancel, and we're done, as this is the required expression. So moving on to another example, we'll look at some slightly more complex questions now. So part 1, use standard series to show this result up here. So this is interesting. We've introduced some kind of constant here, p. Let's see how we can do this. So first part, let's separate out the summation. So this becomes 2r cubed minus pr squared. Remember, r is a constant, and we're taking the sum between r equals 1 and n. So let me split that up into two summations. And we'll take out these multiplying factors of 2 and p out at the front of the summations. And now let's substitute in the standard results. So this one here is n squared over 4 n plus 1 all squared, and then we are subtracting from that p multiplied by n over 6 n plus 1 to n plus 1. Now, we then need to factorise it, so this is in the correct format up over here. So I'm going to take out a factor of 1/6, a factor of n, and a factor of n plus 1. Put in some square brackets here for clarity. Now, for the first part, the 2 and the 4 will simplify to give me a half, so I need to have a 3 here, so that multiplies by the 1/6 to give me a half. I then need an n and an n plus 1. And then we're going to subtract, and we need a p here, and a 2n plus 1. There we go. So we're nearly there. We've got the first part of this absolutely spot on. We just need to simplify the part inside the large red square bracket. So let's do that carefully. So that gives me 3n squared plus 3n minus 2pn minus p. And always look at your final answer here and look at how you aim to get to that final answer. So all we have to do is factorise the n from these terms here. So we get 3 minus 2p multiplied by an n, and then we simply have the subtract p at the end. So that's exactly as required by the question. Now there's an interesting part 2 here. Given that the coefficients of n cubed and n to the power 4 in the expression here are equal, find the value of p. So we're going to need to expand this and find the coefficients of n cubed and n to the power 4. So we have 1/6 n plus 1, 3n squared plus 3 minus 2p n minus p. And I'm going to multiply first by multiplying these and these together. So what do we have? We've got 3n cubed plus 3 minus 2p n squared minus pn. So I've multiplied everything in the quadratic expression by the n from the linear expression before it. And now I'm going to multiply everything in the second bracket by the 1 here. So that gives me 3n squared plus 3 minus 2p bracket n minus p. Notice I stacked my terms so I can see which ones match with which. And then we're going to multiply through by the 1/6 n at the beginning as well. So we've got 1/2 n to the power 4 plus 1/6 3 minus 2p n cubed. Now, I'm only interested in the coefficients of n cubed and n to the power 4. Now, when I multiply n by this pn part here, I'll get an n squared, so I'm not really bothered about that. And in the same way, I'm going to ignore this and not bother multiplying them by the n, because I'm not actually interested in what I'm going to get here. But I am going to ensure that I multiply this here by this part here as well, because that's going to give me a contribution to n cubed. So these two multiplied together, and I'll write them in pink here so we can see, will give me 1/2 n cubed. So the coefficients of n cubed and n to the power 4 are equal. Well, the coefficient of n to the power 4 is 1/2. The coefficient of n cubed is composed of this and this. So we can say that 1/2 is equal to 1/6 3 minus 2p plus 1/2. So from here, well, we can subtract 1/2 from both sides of this equation, which gives us 1/6 3 minus 2p equals 0. 3 minus 2p equals 0, and then p equals 3/2. Okay, one last example. So the first part, really standard by now, show that the sum is equal to n squared. So let's take a look at this. Do this up here. So splitting this up, this becomes 2 multiplied by the sum of r between r equals 1 and n, take away sum of 1. So this, of course, is 2 multiplied by a half n plus 1, take away n, which equals this, which, of course, you can see simplifies to give us n squared when you expand. Okay, now this is more interesting in the second part of the question. Show that this simplifies down to k, where k is a constant to be determined. Now, the top of this you should hopefully recognise as this. Now, the second part is the same sort of summation, because the formula is still 2r minus 1, but you're going from r equals n plus 1 up to 2n. So how do we work that out? Well, we can use this formula here with some adjustment. Now, if I were working out the sum between r equals 1 and 2n of 2r minus 1, well, I would simply replace n with 2n, because that's now the final number of terms. So that would be 2n all squared, which is 4n squared. But if you look at the summation we're doing, we're going from r equals n plus 1 to 2n. So how do I work that out? Well, if I take all of the terms between 1 and 2n and their total summation, and I subtract from that the sum of all the terms between r equals 1 and n, then I will be left with what I want, which is the sum of all the terms between r equals n plus 1 and 2n, like this. Just stop and check for yourself that this makes sense to you. So we have all of the sum of the terms between the first term and the 2nth term. That's what we have here. And we are going to take away the sum of all the terms between the first term and the nth term. So we're taking this part away like that, which of course means we then have the sum of the terms between the n plus 1th term and the 2nth term left like that, which is what we're looking for. So let's work this out. So we know that this part here, this first summation, is equal to 4n squared. We worked it out. Now, this second part here, the sum between r equals 1 and n of 2r minus 1, well, we know what that is. That was the very first part of the question. That's n squared. So this, the sum between r equals n plus 1 and 2n, is going to equal 3n squared. So that's this here. So to finish this off, let's write this out correctly. We are working out the sum between r equals 1 and n of 2r minus 1, and we're dividing it by the sum between r equals n plus 1 and 2n of 2r minus 1. So we know that the numerator of this is equal to n squared, the first part of the question that we worked out, and we know that the denominator of this is equal to 3n squared, which we've just calculated right now, and the n squareds cancel, which leave us with a third, which tells us that k is equal to 1/3. A tricky question, and the key part of this question was this part here. So please make sure you understand exactly how we were manipulating the summations to get the summation that started with an r value of n plus 1.